In this lecture, we're going to talk about systems of linear equations and how to solve them using the substitution or elimination method. First, let's recall that an equation sets two expressions equal to each other. For example, 5x plus y equals 3 would be an equation. So a system of equations will be a collection of two or more equations with one or more variables. For example, 5x plus y equals 3 and 2x minus y equals 4 is a system of two equations with two unknown variables. X plus y plus z equals 6, 3x minus 2y plus 4z equals 9, and x minus y minus z equals 0 will be a system of three equations with three unknown variables. When presented with a system of equations, we want to be able to find the solution to the system. So by definition, a solution of a system of equations is the set of values for the variable which makes each equation true. So whatever you find has to satisfy each equation. If the system has a solution, it's called a consistent system. If there's no solution, then it's called an inconsistent system. So let's look at an example dealing with a solution. We want to verify that x equals negative 2 and y equals 4, which represents the ordered pair negative 2, 4, is a solution to the system of equations 3x plus 2y equals 2 and x minus 7y equals negative 30. So to verify that this is a solution to the system, we need to plug these values into both equations and show that both of them are in fact true. So let's start with 3x plus 2y equals 2. If we plug negative 2 in for x and 4 in for y, we have 3 times negative 2 plus 2 times 4 equals 2. If we simplify the multiplication, that will give us negative 6 plus 8 equals 2. And finally, negative 6 plus 8 is 2, so we get 2 equals 2. This is a true statement, so they are a solution for this one equation. But to determine if it's a solution for the system, we have to check both equations. So we also need to examine x minus 7y equals negative 30. We plug in negative 2 for x, and we plug in 4 for y, giving us negative 2 minus 7 times 4 equals negative 30. If we simplify the multiplication, we'll get negative 2 minus 28 equals negative 30. And negative 2 minus 28 gives us negative 30, so we have negative 30 equals negative 30. This is also true. So the point negative 2, 4 is a solution to the system of equations. Okay, now let's talk about solving a system using the substitution method. To solve a system by substitution, we'll take the following steps. First, pick one of your equations and use it to solve for one of the variables in terms of all of the other variables. All right, substitute your results into the remaining equations. So if you solved one of the equations for x, substitute that into all of the other equations where you see x. If this results in one equation that has only one variable, solve it. If not, repeat steps 1 and 2 until you get one of the equations to have only one variable. After you solve the equation that had only one variable, find the values of the other variables by back substitution. So plugging the variable you know into the previous equations to solve for the other variables. And finally, check your solution to make sure that it makes sense and that it satisfies the system of equations. So let's look at an example where we'll solve using substitution. We have the system of equations 3x plus 5y equals 2 and 2x minus y equals negative 3. The first step is to pick one equation and solve for one variable. So we're going to look at equation 2 and solve for y. Solving equation 2 for y gives us y equals 2x plus 3. So we'll take that result and plug it into the other equation. So we'll take that result and plug it into equation 1. That will give us 3x plus 5 times 2x plus 3 equals 2. We can distribute the 5 to give us 3x plus 10x plus 15 equals 2. 3x plus 10x will give us 13x. And we can subtract 15 from both sides of the equation to get 13x equals negative 13. And if we divide both sides of the equation by 13, we'll get x equals negative 1. So we found the value of one of our variables. Now that we know that x is equal to negative 1, we can take that value and plug it into our previous equation to find the value for y. So if y was equal to 2x plus 3, that means y will equal 2 times negative 1 plus 3, which simplifies to be negative 2 plus 3, which is just equal to 1. So the solution to this system of equations will be the point negative 1, 1. The very last step, which we're not going to do in the lecture, is to take these values and plug them back in to check our answer. Let's look at another example. This time we have the system of equations 4x plus 5y equals negative 3 and negative 2y equals negative 4. We want to start by solving one of the equations for one of the variables. And if we look, we see that the second equation only has one variable. So let's use the second equation to solve for y. So if negative 2y equals negative 4, we can divide both sides by negative 2 to give us that y equals 2. Now that we know what y is, we can plug it into our other equation. So we had 4x plus 5y equals negative 3. Now that we know that y is equal to 2, we can plug that in, giving us 4x plus 5 times 2 equals negative 3. If we simplify, that gives us 4x plus 10 equals negative 3. We subtract 10 from both sides of the equation, giving us 4x equals negative 13. And to solve for x, we'll divide both sides by 4. So we get x equals negative 13 over 4. So the solution to this system of equations is the point negative 13 over 4, comma 2. Again, you can check this answer by plugging them back in and making sure that both equations are satisfied. Next, let's talk about solving a system of equations using the elimination method. So the steps we're going to present here are specifically for a system of two equations. Okay, so the elimination method is called the elimination method because we want to try to eliminate one of our variables. So the first step is, if necessary, multiply one or both equations by a constant so that when you add the two equations together, one of the variables will cancel out. After you add the equations together, you will have an equation of one variable which you can solve. After you solve the first variable, take it and plug it into one of the two equations you started with, and solve to find the other variable. Note that if you wind up with a statement that is always true, like 5 equals 5, then there are going to be an infinite number of solutions, and the system is said to be dependent. If you encounter a statement that is never true, like 5 equals 0, then there are no solutions, and the system is inconsistent. So let's look at an example. For this example, we have x minus 3y equals 2 and 6x plus 5y equals negative 34. We want to make it so that when we add the two equations, one of the variables will cancel out. And one strategy is to always try to work with a variable that doesn't have a coefficient. That makes it easy to deal with. So if we look at this equation, the second equation has 6x, and the first equation just has an x. So we could multiply the first equation by negative 6, which would change the first equation to be negative 6x plus 18y equals negative 12. And now you see the first equation has a negative 6x, and the second equation has a positive 6x. So if we add the equations together, the 6x's will cancel out. So let's add the equations together. Negative 6x and 6x cancel out. 18y plus 5y gives us 23y, and negative 12 plus a negative 34 will give us negative 46. Now we have an equation that just depends on y, so let's solve for y. If 23y equals negative 46, we can divide both sides by 23 to get y by itself, so y equals negative 46 divided by 23, which simplifies to be negative 2. Now that we know what y is, we'll plug the value for y into one of the equations that we started with and solve for x. It doesn't matter which equation we use, so let's use equation 1. It looks a little bit simpler. If we plug the value of negative 2 in for y, that'll give us x minus 3 times negative 2 equals 2. We simplify negative 3 times negative 2 as a positive 6, so x plus 6 equals 2. We'll subtract 6 from both sides of the equation, and we get x equals negative 4. And so it looks like our solution will be the point negative 4, negative 2. Let's look at another example. So this time we have the system of equations x plus 3y equals 5 and 2x minus 3y equals negative 8. Again, the goal of the elimination method is to multiply one or both equations by a constant so that when we add them together we can eliminate one of our variables. If we wanted to eliminate x, we could multiply the first equation by negative 2. However, if we look at this, our y's already are opposite. I have 3y in the first equation and negative 3y in the second equation. So in this example, we're going to cancel out our y. We don't need to multiply either equation by any constant. We just need to add them together. So x plus 2x gives us 3x, and 3y minus 3y cancels out. 5 plus a negative 8 gives us a negative 3. Now we have an equation that just depends on x, so we should be able to solve for x. If 3x equals negative 3, we can divide both sides by 3 to give us x equals negative 1. Now that we know the value of x, we can plug that value into either of our original equations and solve for y. So I'll use equation 1, x plus 3y equals 5. We plug negative 1 in for x, so we get negative 1 plus 3y equals 5. To solve for y, we'll add 1 to both sides of the equation, which gives us 3y equals 6. We'll divide both sides of the equation by 3 to give us y equals 2. And so the solution to this system of equations is the point negative 1, 2. Now we'll look at an example that results in an inconsistent system. We have the system of equations x minus y equals 5 and negative 3x plus 3y equals 2. We can try to solve this system using either the substitution or elimination method. I'm going to continue using the elimination method. So to eliminate a variable, we have a negative 3x in the denominator. To eliminate x, we could multiply the first equation by 3. So that would give us 3x minus 3y equals 15, and negative 3x plus 3y equals 2. We'll add the two equations together. 3x plus a negative 3x cancels out to give us 0. Negative 3y plus 3y cancels out to give us 0. And 15 plus 2 gives us 17. So we wind up with the equation 0 equals 17. Well, that's inconsistent because 0 doesn't equal 17, and therefore this system does not have a solution. So there are no solutions to this system. Note that the graph of an inconsistent system is going to be represented by a pair of parallel lines. Now let's look at an example that's going to result in a dependent system. We have 3x minus y equals 7 and 9x minus 3y equals 21. I'm going to continue using the elimination method, so if I want to eliminate my x variable, I'll multiply the first equation by negative 3. So that'll give us negative 9x plus 3y equals negative 21, and 9x minus 3y equals 21. We'll add the two equations together. Negative 9x plus 9x cancel out, leaving us with 0x. 3y plus a negative 3y cancels out, giving us 0y. And negative 21 plus 21 cancels out, giving us 0. So when we add our two equations together, we get 0 equals 0. And so this system will be dependent because 0 always equals 0. So our solution will be the set of all xy such that 3x minus y equals 7. If we want to present the solution as an ordered pair, we need to solve one of the variables in terms of the other. So if we start with equation 1, 3x minus y equals 7, we can solve that for y, which gives us y equals 3x minus 7. And so we can express our solution as the ordered pair x, 3x minus 7. Note that the graph of a dependent system is represented by overlapping lines, or each equation represents the same line. So far we've worked with systems of two equations with two unknowns. Now we're going to move up to a system of three equations. So this will be the process we use for solving systems with three variables and three equations. First, we'll use the elimination method with two of the three equations to get rid of one of our variables, say x. Second, we'll use the elimination method with a different set of two of the three equations to get rid of the same variable, x. So from step 1 and 2, we've created two new equations that only have two variables. So step 3 is to eliminate one of those variables, let's say y, using the results from steps 1 and 2. Now we should have an equation that has just one variable, z. So we should be able to solve for the variable z. Once we know what z is, we can plug its value into one of the equations from step 1 or 2 and solve for y. And then finally, we'll plug the values that we know for y and z into any of the original equations and solve for x. Let's look at an example where we'll solve a system of three equations with three unknowns. We have x plus y plus z equals 6, 2x minus y minus z equals negative 3, and x minus 2y plus 3z equals 6. First, we want to use the elimination method on two equations to eliminate the x variable. So I'm going to multiply the first equation by negative 2 and add it to the second equation. This will give us negative 2x minus 2y minus 2z equals negative 12, and 2x minus y minus z equals negative 3. We add the equations together. Negative 2x plus 2x cancel out. Negative 2y plus a negative y equals negative 3y. Negative 2z plus a negative z equals negative 3z. And negative 12 plus a negative 3 gives us a negative 15. So now we have an equation that just has two variables. Next, we'll use the elimination method on a different two equations to eliminate x. So we'll multiply the first equation by negative 1 and add it to the third equation. This gives us negative x minus y minus z equals negative 6. X minus 2y plus 3z equals 6. We add the equations together. Negative x plus x gives us 0. Negative y plus a negative 2y gives us a negative 3y. Negative z plus 3z gives us 2z. And negative 6 plus 6 gives us 0. So we're left with the equation negative 3y plus 2z equals 0. So now we'll use the elimination method to solve this resulting system of two equations. We'll multiply the second equation by negative 1 and add them together. So multiplying the second equation by negative 1, so we can cancel our y's, will give us the system negative 3y minus 3z equals negative 15, and 3y minus 2z equals 0. We add our two equations together. Negative 3y plus 3y gives us 0. Negative 3z plus a negative 2z gives us negative 5z. And negative 15 plus 0 gives us negative 15. So we're left with the equation negative 5z equals negative 15. If we divide both sides of the equation by negative 5, we wind up with z is equal to 3. Now that we know that z is equal to negative 3, we can plug it into one of the two equations above to solve for y. So I'll plug it into the second of the two equations we found, negative 3y plus 2z equals 0. So we have negative 3y plus 2 times 3 equals 0. If we simplify, that gives us negative 3y plus 6 equals 0. We subtract 6 from both sides of the equation, so negative 3y equals negative 6. And then divide both sides of the equation by negative 3, giving us y equals 2. So now we know z equals 3 and y equals 2. So now that we know that y equals 2 and z equals 3, we can plug these values into any of the original equations to find our value for x. So I'll use the equation x plus y plus z equals 6. If we plug in the values for y and z, that'll give us x plus 2 plus 3 equals 6. If we simplify, we'll get x plus 5 equals 6. We subtract 5 from both sides of the equation, giving us x equals 1. The last thing we want to do is write the solution as an ordered triple. So the solution to this equation will be x equals 1, y equals 2, and z equals 3, which can be written as the ordered triple 1, 2, 3. Let's look at one more example. This time we have the system of equations 2x plus y minus 3z equals 1, x minus 4y plus z equals 6, and 4x minus 7y minus z equals 13. We'll start by using the elimination method with two equations to eliminate x. So let's multiply the second equation by -2 and add it to the first equation. This will give us 2x plus y minus 3z equals 1, and multiplying the second equation by -2 gives us -2x plus 8y minus 2z equals -12. We'll add these two equations together. 2x plus a -2x cancel out. Y plus 8y gives us 9y. -3z plus a -2z gives us -5z. And 1 plus a -12 gives us -11. So we have the equation 9y minus 5z equals -11. Next, we'll use the elimination method with a different two equations. So looking at equations 2 and 3, let's multiply equation 2 by -4 and then add them together to cancel x. Multiplying equation 2 by -4 gives us -4x plus 16y minus 4z equals a -24. And equation 3 is 4x minus 7y minus z equals 13. We'll add the two equations together. -4x plus 4x will cancel out. 16y plus a -7y gives us 9y. -4z plus a -z gives us -5z. And -24 plus 13 gives us -11. So we get the equation 9y minus 5z equals -11. And now we want to try to solve the resulting system of two equations. So we'll multiply one of them by -1, so we'll have 9y minus 5z equals -11, and -9y plus 5z equals 11. We add them together, and we see that all terms on both sides of the equation cancel out. We wind up with 0 equals 0. 0 equals 0 is always true, so this will be a dependent system with an infinite number of solutions. So let's try to get all of our solutions in terms of the variable y. First, we'll let y equal y and find out what z would be. So if we have 9y minus 5z equals -11, we can solve that for z. We'll subtract 9y from both sides of the equation, giving us -5z equals -9y minus 11. And then divide both sides by -5, giving us z equals 9y plus 11 over 5. Now that we have values for y and z, we'll plug both of those into one of our original equations to solve for x. So, we'll use the second equation, x minus 4y plus z equals 6. Plugging in the values that we previously found, we'll get x minus 4 times y plus 9y plus 11 over 5 equals 6. Since we're solving for x, we'll rewrite everything else with a common denominator of 5. So 4y we can rewrite as 20y over 5, and 6 we can rewrite as 30 over 5. We can combine -20y over 5 plus 9y plus 11 over 5 by combining the y terms. So 20y, -20y plus 9y gives us -11y. So that gives us x plus -11y plus 11 over 5 equals 30 over 5. To solve for y, we'll subtract -11y plus 11 over 5 from both sides of the equation. And if we simplify, we'll get x equals 11y plus 19 over 5. So plugging in these results for x, y, and z, we'll get the ordered triple 11y plus 19 over 5, comma y, comma 9y plus 11 over 5.